This is a presentation of the paper How They Did It, an analysis of emissions defeat devices in modern automobiles. It's presented by Chris McGehee for the course Introduction to Cyber Physical System Security for Georgia Institute of Technology. The authors of this paper are the following. I'll do my best to pronounce their names correctly. Moritz Kontag, Guo Li, Andrei Pawlowski, Felix Domke, Kirill Levchenko, Thorsten Tolles, and Stefan Savage. And they are from the Ruhr-Universität Bochum in Germany, as well as from the University of California in San Diego. And this paper was published in May of 2017. Some context for this paper. In 2015, the United States Environmental Protection Agency found that Volkswagen was guilty of cheating on their emissions testing, and they were eventually fined $2.8 billion. So the problem is that while in emissions testing mode, the Volkswagen vehicles emitted far less pollutants than was allowable. When they were in driving mode outside of testing, they emitted levels of pollutants that were far higher than the allowable limits, in some cases up to 40 times the amount of nitrogen oxide that was allowed. So this paper introduces a software verification technique that can be used to help find cheating in these emission tests. There's also another automaker, Fiat, which has been found to have been used a cheating device, and the authors contend that it is likely that the manufacturer Bosch originally created these defeat devices and that the car makers adapted the software of these defeat devices to be able to work for their individual vehicles. So the way that these emissions are tested is that the vehicle follows a predefined driving profile of speed and hills, going up and down hills and turning and stopping and starting. And these profiles are all published ahead of time, so the automakers get to see how they will be tested. And this is done to ensure that everyone is given a fair and accountable process, that everyone is treated the same with these tests. And this is a form of black box testing, in that the inputs, the driving conditions, are given to the vehicle, and then the output, in this case the emissions, are measured from the vehicle. And this black box testing is the only kind of testing that is given to these vehicles to ensure that they meet emission standards. And the authors of this paper argue that this is insufficient for modern vehicles, which are complex computing systems that often contain more than 100 million lines of code in them. So a little bit about how diesel engines work. So in contrast to a gasoline engine will inject a mixture of air and fuel into the cylinder, and then the spark plug will ignite the air and the fuel, which then expands the cylinder and gives power to the crankshaft. And this is in contrast to a diesel engine, in that a diesel engine will compress the air, and then the fuel is injected into the compressed air, and the fuel ignites solely on the basis of the compression, and there is no need for a spark plug to ignite the fuel. And so as a result of this different mode of ignition, it is possible that diesel has higher levels of some pollutants when fuel is not fully combusted. And these two particular pollutants that we will discuss is particulate matter, which is also known as soot, and that's the gray stuff that you see from coming out of a tailpipe, usually an older car that hasn't been maintained very well. And then the other pollutant is nitrogen oxide, which is, the chemical formulas are either NO or NO2, and those are often both abbreviated just as NOx, which you see here on the slide. And both of these pollutants are byproducts that damage the human respiratory tract that can lead to lung disease and heart disease, among other problems. So they are limited for very good reason for our human health. And because of these pollutants that diesel generates, these diesel engines have certain controls on them to reduce the pollutants that are eventually emitted. One of them is called exhaust gas recirculation. And the way that this works is that some of the exhaust gas that comes from after the fuel has been combusted, it gets recirculated into the air intake and then injected with fuel again and used to expand the cylinder. And this has the effect of increasing soot, but it has the beneficial effect of decreasing nitrogen oxide. And another emission control is nitrogen oxide storage catalyst. And what this does is that it will do a chemical reaction to store some of the nitrogen oxide out of the exhaust, which is good because it reduces nitrogen oxide. But the catalyst periodically has to regenerate itself using a rich fuel-air mixture. And while this regeneration is occurring, the engine is less efficient and it produces more soot. The third emissions control is called selective catalyst reduction. And what this component does is that it injects urea into the exhaust. And one of the downsides to this is that eventually the urea will need to be replenished. But this does have the effect of reducing nitrogen oxide, which is good. And the last emissions control covered is called the diesel particulate filter, and this traps soot from the tailpipe, and it also has a regeneration cycle, and this regeneration cycle needs to be run for a fairly long period of time, 10 to 15 minutes, and if that time period is not run long enough, then the filter will need to be replaced. So this filter could be needing to be replaced fairly often if the vehicle is traveling short, quick trips just around town. And as you can tell from the name of the component is that it reduces soot or particulate matter coming out of the engine. The way that these tests are conducted is that the vehicle is mounted onto a chassis dynamometer, and the chassis dynamometer is a raised platform where the vehicle is kept stationary and the wheels are allowed to move, and then they can turn and they sometimes have resistance applied to them, and this allows the test for emissions to be administered in a controlled manner right there inside the laboratory. And these tests will define the speeds that the vehicle is to go on, as well as whether it's going uphill or downhill, and turning conditions and everything else that is needed to perform a complete driving experience. And as the driving is going on, the emissions from the vehicle are measured, and the emissions are compared to the standard to see if they are below the allowable limit. And so an example test would be a simulation of an urban route with frequent stops. This one lasts 31 minutes, covers 11.04 miles, and its average speed is 21.2 miles per hour with plenty of stopping, going down to 0 miles per hour and accelerating. And the emissions are measured at the end of that test. So in the cars there is something called an engine control unit, and it's an electronic component that's responsible for essentially running the engine. And the engine has lots of sensors, and actuators, and so the engine control unit reads in these sensors and performs actions on the actuators to control the rate of the revolutions and to also configure the emissions controls that are operating to reduce emissions from the engine. And both Volkswagen and Fiat use the EDC17 ECU, which is created by the manufacturer Bosch. And so Bosch is the one that builds the hardware and creates the firmware for these engine control units. And then the automakers, what they do is that they just modify certain constants in the firmware, and the automakers don't actually write any of the firmware themselves or make any modifications to the firmware as far as the authors could tell. And this shows that this could be evidence that Bosch is the one who originally created these defeat devices, and then the automakers essentially just turned them on and activated them so that the emission testing could be avoided while the car was not under an emissions test. So the researchers gathered certain materials to do their analysis on, and one of these is something called function sheets. And what a function sheet is that it documents the behavior of the firmware constants in an engine control unit, and this helps the automakers determine what values they want to set for their particular vehicle. And the researchers did not obtain these documents from Bosch nor from the car makers. They actually found them on online portals where car enthusiasts go to share tips and tricks about how they tune their cars to increase performance and other things. And another type of file that these researchers found were A2L and OLS files. And these files contain debug information for the firmware images for the engine control units. And these are similar to like a PDB file on a Windows operating system that contains information to help the programmer debug program when it is running or when it crashes. And these were also obtained from car tuning websites. And finally, the researchers analyzed the actual firmware image, the software that is running on the cars that controls the engine. And these were obtained actually from Volkswagen, because Volkswagen maintains an online portal where for car repair specialists to log in and download these firmware images to help them as they repair their cars and their shops. And these firmware images are the ones that the researchers later used as part of their input to their software verification. So a defeat device, what that is it is a mechanism that causes the vehicle to behave differently on the road than in an emissions test. And a defeat device contains two components. First off, it will try to determine if the current driving conditions can rule out an emissions test. And secondly, if it sees that it is not under a test currently, then it will modify its behavior to perform certain characteristics differently. And an example from past decades of a defeat device was when General Motors used whether or not air conditioning was turned on in their Cadillacs to rule out that they were in an emissions test back in the 1990s. So at that time, all of the emissions testing that were performed with the air conditioning off. So then General Motors programmed their Cadillacs to detect if the air conditioning is on, and that means it's not inside of an emissions test, so then it can have higher levels of pollutants. And so with the Volkswagen defeat device. The way that it tested whether or not it was inside of a test was it was represented in the code by a function block named customer specific acoustic condition. So of course there was not a variable inside their code that says is under emissions test, because that would be a bit suspicious if someone were to peruse the documents and find a variable with that name in there. So they decided to use something a little bit more ambiguous to determine whether or not they're in an emissions test. And so what this condition does, or how it works, is that when the engine first starts up, it will be set to testing mode based on measurements of temperature from the coolant, from the air, and from the oil, as well as the atmospheric pressure. And this is when the engine is turned on, because these variables are known what they're going to be in an emissions testing, so it can help to determine whether the vehicle is in fact inside of an emissions test. And then when a vehicle first gets started in testing mode, it can later get switched to normal mode based on several criteria. And the first criteria is the time that has been elapsed since the pedal accelerator has reached a certain threshold. And then another criteria is the number of engine revolutions has reached a certain threshold. And last criteria is that the time and the distance traveled falls outside of a certain curve. And we are going to talk about these curves here next. So the firmware will use the time and the distance that is traveled and to create an XY coordinate and it will see if that XY coordinate falls within a certain curve profile, if it falls within a certain region of a graph, you could say. And so the researchers found 7 different curves inside the firmware that matched over a dozen known tests. And the way this works is that if the time and the distance falls outside of each of the 7 curves at least one time, then the defeat device can determine that the test has been ruled out. Then it can switch to normal driving mode and start emitting higher levels of pollutants. So you'll see in these graphs, these are a representation of these curve profiles as found in the firmware. And the white part of the graph represents a portion that's inside the curve, which means that it possibly is inside of an emissions test. And then the gray portion represents being out of the curve, which means that it's possible that it is not within a test. So if we look at the top left graph, you'll see that the white portion follows the red line, and this red line is an actual emissions test with the known time and distances traveled. And you can look at different points in the graph to determine whether it's inside or outside the curve. So let's say we look at 600 seconds at 6 kilometers. So if we've traveled 6 kilometers at that time, then we see that we are inside of the curve. And then we know that we probably that we could be inside of a test, inside of this particular test. But let's say that at 600 seconds, we have only traveled 2 kilometers. So 2 kilometers falls inside of the gray region here. So that means that we are not inside of this particular test right here, and then we can rule that test out. And as you see from the following graphs, there are several different profiles, curve profiles, that match several different identified known tests. And some of them match tests more closely than others. Some of these profiles match a large number of tests, like the one on the bottom right, Some of them only match 1 or 2 tests. And what this Volkswagen defeat device does when it rules out that it's inside of a test is that it will modify fuel injection to increase power to the engine. And also what it will do is that it will lower the amount of gas that goes into the exhaust gas recirculation. So this will increase nitrogen oxide, it will decrease soot levels, and with decreased soot levels coming from the engine, this reduces the load on the diesel particulate filter. And with a lower load on the diesel particulate filter, then that lowers the maintenance burden, because then the owner of the vehicle does not have to go and get the filter replaced as often, which gives greater convenience to the driver. And unfortunately, Volkswagen is not the only automaker that has been found to have used defeat devices. In the Fiat 500X, this vehicle, at the time of this paper was written, was under investigation from the European Union for using a defeat device to cheat on emissions testing. And this was a simpler defeat device. It was triggered after 26 minutes and 40 seconds, because that is a time that most emissions tests are shorter than. So after that time, it can generate higher levels of pollutants. And it does this by reducing the regeneration cycle of the nitrogen oxide storage catalyst. And the storage catalyst, when it regenerates, it has to use higher levels of fuel inside of the catalyst, and that reduces performance, which drivers do not like when that happens. And this mechanism was first documented in this paper, and a couple of years later, Fiat settled for $500 million as a result of this defeat device and their cheating on emissions testing. So to detect these defeat devices, the researchers created a tool to find driving profiles in the firmware and compare those to actual test profiles. So those were like back a couple slides when we looked at the graphs. It had the gray regions and the white regions, and the tests were inside of the white regions. This tool can analyze code to find those driving profiles and match them to test profiles. So as you can see, this is a form of static code analysis. It's different than the black box testing, where the vehicles are spinning in a stationary location. And the researchers were able to demonstrate that this tool is time effective, in that it only takes on average 2 minutes to analyze a firmware image and decide whether or not it has any driving profiles that matches testing profiles. And they analyzed 963 different Volkswagen images and found that 406 of them contained code in there to detect a driving profile and alter the behavior. So this tool is also shown to be effective in catching defeat devices. So the researchers wanted the reader to draw several conclusions. One is that black box testing has its limitations, in that in today's automobiles, there are ways for car makers to easily avoid emissions testing by programming defeat devices in the software. And so because of this, software analysis has potential to help with measuring emissions testing and make sure that vehicles are following the proper emission standards. And the researchers wanted to point out that companies have huge incentives to cheat on tests. So one thing that governments can do is use the software verification technique presented in this paper to better analyze whether or not a vehicle is going to meet emission standards out while driving in the real world.